It's time to talk about circular motion. We're going to start off with uniform circular motion. That's an object moving in a circular path at constant speed. Here's a circular path, and if my object is over here at some instant in time, it's going to have some velocity. If it's moving around the circle counterclockwise, then at that instant it's going to have a velocity that points in this direction. Let's call that v1. Well, at some later time, the particle's going to be over here somewhere. And it's going to have a velocity that points in this direction. We'll call that v2. And at some later time, maybe it's up here, it has a velocity that points in this direction. We'll call that v3. And our definition of acceleration is this. Our definition of acceleration is this. The average acceleration is the final velocity minus the initial velocity over time. One thing we know about this, if it's moving at a constant speed, we know that v1 magnitude equals the magnitude of v2 equals the magnitude of v3. So if we have v final minus v initial, so in the time interval between 1 and 2, v2 would be our final velocity and v1 would be our initial velocity. So v2 minus v1 is the same as v2 plus the opposite of v1. I'll use green. So the opposite of v1 would point like this. And then my acceleration vector is going to be proportional to this red vector here. This red vector is equal to v2 minus v1. I have to divide by time to get the acceleration. But this is proportional to my acceleration, and it points in the same direction as my acceleration. And what direction is it pointing? Toward the center of the circular path. Let's do this one more time. Let's take the time interval from 2 to 3. So 3 is our final time, and 2 is our initial time. And we start with v final, which is right here. And then we're going to subtract v initial, which is v2. So the opposite of v2 is going to point in this direction, roughly. And when I subtract those two vectors, I get this red vector, which points toward the center of the circle. And it's proportional to the acceleration. I have to divide by time to get acceleration, but it's proportional to the acceleration. And it points in the same direction as the acceleration. That's the important thing here. And this makes sense because if I have an object and it's moving in a straight line, and I want to change the speed of the object, I have to apply a force in the direction of motion or opposite the direction of motion to change the speed of that object. If I want to change the direction it's moving, I have to apply a force perpendicular to the direction of the object to change its direction of motion. So if my object is coming along here in this direction, and at some point it's here, and I give it a big push in this direction, what's going to happen? It's just going to move faster in that direction. If I give it a big push in this direction, it's going to slow down. But the direction is not going to change. Only the speed will change. If my object is moving along here with speed v, and I give it a kick with my foot in this direction, what's going to happen to my object? Well, it's going to end up over here moving with the same exact speed v, but now it's going in a different direction. I can't change the speed of the object by pushing perpendicular to its velocity. I can only change the direction. And I can't change the direction by pushing parallel to the velocity. I can only change the speed. So if I have an object that's moving in a circular path with constant speed, my force has to be perpendicular to its path, has to be perpendicular to the tangent line. There can't be any force that's tangent to the path, or it would change the speed. All the forces have to be towards the center of the circle to keep changing the velocity to get it to move in a circular path. So there's always a net force acting on it toward the center of the circle. That's the direction of the acceleration. And we give that a special name. When we know something is moving in a circular path, there's something special about the acceleration. The acceleration in the radial direction. So what's the radial direction? That's toward the center of the circle or outward, the radial direction. What's the tangential direction? That's tangent to the circle. The acceleration in the radial direction is equal to a special value v squared over r. And we call that a centripetal. That's the centripetal acceleration. That's the acceleration of an object moving in a circular path. And what's the direction? Toward the center of the circle. Some students get a little confused with something that people call centrifugal acceleration. That's a force that doesn't really exist. The centrifugal force doesn't really exist. It feels like you're being pushed outward when you're in the rotating frame. So if you go to the amusement park and they have a big cylinder there, and you stand in the cylinder with your back up to the wall, and the cylinder spins around and the floor drops out and you're stuck up against the wall, how does it feel to you when you're in the rotating frame? When you're standing there in the cylinder, spinning around, it feels like you're being pressed up against that wall, like something is pushing you into the wall. It feels as if there's an outward force on you. But think about it for a second. Is there something here pushing out on you? No. Can the wall grab you and pull you into the wall? No, walls can only push, they can't pull. So what's going on? There's no outward force. We call it a fictitious force because it doesn't exist. It just feels that way when you're in the rotating frame. What's really happening is that your body is moving in this direction at some instant in time. Your body has inertia. And it wants to go in that direction. It wants to go in a nice straight line in this direction. But what happens? The wall gets in the way, and the wall pushes in on you. As your body tries to go in a straight line, the wall pushes in on you. And so you feel as if you're being pushed into the wall. But really, it's just your body's inertia wanting to go in a straight line, and the wall pushing in on you to change the direction of your velocity and keep you moving in a circular path. It's just like this. If you're sitting in a car at a red light and the light turns green and you hit the gas a little too fast, the car lunges forward. And what does it feel like when you're sitting in that car? It feels like something pushed you backwards into the seat. But did something push you backwards into the seat? No. There's no force pushing you backwards. Your body has inertia. It wants to stay at rest. It's sitting there at the red light. It wants to stay at rest. And the light turns green. The car lunges forward. And your body needs a certain force to get it to accelerate with the car. So you sink into the seat cushion a little bit until the spring force builds up enough force to keep you accelerating at the same rate as the car. You never go backwards. The car lunges forward, your body resists that a little bit, and then your body moves with the car when the force from the springs builds up enough to accelerate your body with the car. Someone standing outside the car watching you doesn't see you pushed back into the seat. They just see you sitting there and then the car pushing you and you accelerating away with the car. It's the same when you're in that rotating frame of reference. There's no outward force. There's only an inward force, a centripetal force, pointing radially inward, and a centripetal acceleration. One more point I want to make about centripetal force. This is not some new force we're learning about. It's not like, oh, we learned about normal forces and gravitational forces and tensions and friction forces and now a centripetal force. And no. This is a special name we give to the net force in the radial direction when we know something is moving in a circular path. We call it the centripetal force because we know it has a special value. It has the value of m times a centripetal, which is mv squared over r. It's not a new force. It's the same forces we've been seeing. For example, if this is the Earth and we put up a satellite, what do we do when we launch a satellite? We give it a push, give it an initial velocity, and we let gravity do the rest. Gravity pulls on it, and the next thing we know, our satellite is actually over here, moving this way. And gravity pulls on it, and the next thing we know, it's over here, moving this way. And gravity pulls on it, and so the only force acting on our satellite is the force of gravity. The force of gravity has a special value equal to mv squared over r if our object is moving in a circular path. And so we give it a special name. We call it the centripetal force, the force keeping the object moving in a circular path. But it's not some new force. It's just gravity in this case. Let's take a look at another example. When you're in your car and you want to drive around a corner like this. This is circular motion right here for a quarter of a turn as you make that turn. What causes your car to move in that path, in that circular path? Well, there has to be a force in this direction. And what is it? It's the force of static friction between your tires and the road. It's not some new force. It's not some new centripetal force. It's the same friction force we know and love all quarter. We've been dealing with it. Friction keeps your car moving in a circular path. It's just that we know what that value has to be. If your car is moving in a circular path, we know this has to have a special value, mv squared over r. So we give it a special name. We say it's the centripetal force keeping your car moving in that circular path. What if you have a toy airplane on a string? You got some kind of a toy airplane on a string, and it's going around in a circle. You're swinging it around and around and around on a circular path. What's keeping this moving in a circular path? The tension in that string. It's not some new centripetal force, some new force. It's tension in a string. We've been dealing with strings with tension in them. It's tension in the string. It's just that we know it has some special value. What special value does it have? mv squared over r. What's m? The mass of our object, the mass of our toy airplane. V is the speed. And r is this radius. the radius of its path. So we know the force, the net force in the radial direction has to have this special value, m times a centripetal, when something is moving in a circular path. And we give it a special name, a centripetal, F centripetal, circular motion.